Hello, this is a short little talk I'm doing to try to answer the question of how many Raptors do we need on Super Heavy for Starship's first orbital flight. So, the initial plan for Super Heavy, or the real plan, is 28 Raptors, as you can see there. But Musk has said that they won't launch with a full complement of Raptors initially. And that got me thinking about how many Raptors it would actually take to launch an empty Starship, rather than, the full payload Starship. And then I thought that maybe I could actually model it and come up with a guess. So that's what this talk is about. And it's a somewhat educated guess. Some of the numbers that feed into this are probably pretty good. Some of the numbers that feed into this are probably not very good. And there are certainly many things about Starship and Super Heavy that we don't know. So just take this as a little better than throwing a dart at a dartboard. And originally I went through all of the calculations and how I figured this out. And then I realized some people might just be coming here to see what the number is. So I decided I'd do the reveal of the number first, and then I'll go and talk about what I did to get to that number. And those of you who just care about the number can watch to hear and leave. So the number that I came up with is here, a whole bunch of different even numbers. Look at these numbers and see what you think your guess is. If you have an odd number, I'm sorry, you're wrong. So just choose an even number that's close to it. So, hope you have a number in mind. Here's the big reveal. Not 28, not 22, not 14, not 20, 24, 26, 12, 10, or 16. So the estimate is 18. So now if that's all you cared about, you can go away, and on the internet you can now say that, some dude who doesn't know much said it was 18. For those of you who are interested in how I got the number, let's go into that. And what I did was I started by doing some calculations on Falcon 9 on the assumption that Starship and Super Heavy is going to be kind of similar to how Falcon 9 does things, and especially the split in how much energy you get from the first stage and the second stage is going to be similar, because they're trying to land Super Heavy the same way they try to land the first stage of Falcon 9. And then I'm going to, for Starship and Super Heavy, build what I'm calling a reference model in a spreadsheet. And by reference model, I mean based upon the Starship with 6 Raptors, 3 sea level, 3 vacuum, 100-ton cargo, and then the Super Heavy with 28 sea level Raptors. And the reason for doing this is to compare it to Falcon 9 and just to see if it makes sense. And then once we have that, then we will be able to look at this and switch around the reference model so it has no cargo or no payload, and see what numbers we get out. So what does Falcon 9 look like? Well, since the 100-ton cargo is kind of the high end for Starship, we want to look at a high-end cargo mission for Falcon 9, and Starlink seems to be the most likely candidate. So we're going to look at Starlink as an example. And starting with the second stage, we have some specifications. Empty mass is about 3,900 kilograms. Propellant mass, 111,000 kilograms. Payload mass, the Starlink satellites, 15,600 kilograms. The engine on the second stage is a Merlin vacuum, and it has an ISP, or specific impulse, of 348. And you can think of ISP kind of like fuel economy for the engine. It's a good analog. And it has a thrust of about 100,000 kilograms. So we can take all of this and we can plug it into the rocket equation. And that's going to tell us the delta V. And the delta V is simply kind of like a measurement of how far you can go on with a given vehicle. So ISP, specific impulse, I talked about that. 9.8 is kind of inherent in how ISP is calculated. And then ln is the natural log. And then inside ln we have this ratio. And the ratio is the mass of the vehicle at the start. So when you start using it, divided by the mass at the end. So the mass at the end is your empty mass plus your payload. And then the mass at the start is the same as the mass at the end plus propellant. So basically you can think of this as the ratio between the total weight of the vehicle to how much it'll be when the propellant's all gone. So I'll do some math here, plugging in numbers, and then we end up with a delta V of 6,496 meters per second. Now, I probably should have just said 6,500 meters per second. There's certainly not 4 digits of precision here. There might not even be 2 digits of precision here. But that's what I chose to do. And then we have a thrust to weight. The thrust of the engine divided by the total weight when we start is 0.77. And that's pretty typical for a second stage. The kind of second stage Falcon 9 is. You will see some second stages that have thrust to weights much lower than that. And it kind of depends upon how you do trajectories and how you choose to build your first stages and your second stages in terms of size. So that's the second stage. Let's go and look at the whole package. So the first stage with the second stage on top of it. And once again, some specs: empty mass, 27,000 kilograms, propellant mass, 418,000 kilograms, payload mass, which is just a fully fueled second stage with payload, 131,000 kilograms. And then the engines, we're using the Merlin sea level engine. The ISP at sea level is 282. The ISP in vacuum is 311. And since the launch goes from sea level pretty much to vacuum, I just decided to use the average for my calculations. That's wrong. It's not terribly precise, but it's probably precise enough. And then the thrust of a Merlin 1D is 86,000 kilograms. So we'll do the same set of calculations, and we get a delta V of 3,765 or 3,800 meters per second. And you might ask, why is the delta V so much lower? And it's actually very simple. The ratio of starting mass to ending mass is much lower than the second stage. And that's mostly because we're carrying that fully fueled second stage along with us. And the thrust to weight, we have 9 Merlins. So the thrust to weight is about 1.34. And that's a nice kind of hefty thrust to weight. So now that we know what our first stage and second stage can do, we can come up with our delta V budget. So first stage, second stage, add it together, and we get about 10,200 meters per second of delta V. Now getting to orbit is somewhere in the range of 9,000 to 9,400 meters per second. Depends upon thrust to weight, it depends upon the trajectory you fly. So we can see that we can get into orbit with this system, and we have some left over, and that leftover is devoted to the first stage landing. In this case, since we're looking at Starlink, it's a first stage landing on a drone ship. So this gives us a idea of where to start with Starship. And Starship, I'm going to say 9,200 meters per second to get to orbit, and then 200 meters per second for landing. Now initially I had a much bigger number for landing. I had 500 meters per second because that seemed just somewhat reasonable. But last week or so, Musk sent out a tweet, and he said that Starship basically only used about 5% of its propellant for landing, and we can go back and run the numbers with the rocket equation on the amounts he quoted, and that gives us about 200 meters per second. So that's what I'm using here, 9,400 meters per second. to get Starship into orbit and bring it back. So to do this, we're going to need some engines, and obviously they're going to be the Raptor engines. And I got some nice numbers from R. Davis 9 on NASAspaceflight.com forums. These are estimates that came out of a prediction program. So they are probably relatively pretty good. So the Raptor sea level engine has an ISP of 333 and a thrust of 203,000 kilograms. In vacuum, that same engine has a ISP of 355 and a thrust of 217,000 kilograms. And it will be used in both of those cases, since it's used both on Super Heavy and on Starship. We also have the Raptor vacuum engine. It has much higher ISP because it has a much bigger nozzle on it, so about 380, and it has thrust a little bit higher because of that, 229,000. Now masses, we do not have good numbers on. I just kind of arbitrarily threw 2,000 kilograms at each of these motors. It's obviously wrong in that the Raptor vacuum has a much bigger nozzle, and that's going to just inherently weigh more. But it's not going to make a big difference. The sea level Raptor is probably a little less than this. The Raptor vacuum is probably a fair bit more than this. So all of this went into a spreadsheet that I built. And this is pretty simple. On the left side here, we have a bunch of specifications for Starship, how much it weighs, what the ISPs of the Raptors are, what their thrust is, and then we have a section down here for Super Heavy. And then we have a section here where we can kind of play a bunch of what-if games. So choose how many Raptors of each type we have, what our payload is, and then finally we get over to delta V calculations and thrust to weight calculations, which are what's going to come out of this. And then we'll have the same thing for Super Heavy down in this section. So lets me play what-if games. So what did we get for Starship? Empty mass, going to do the same approach we did for Falcon 9. 120,000 kilograms, 100,000 kilograms for payload, 1.2 million kilograms for propellant. Gives us a delta V of 6,700 meters per second and a thrust weight of 0.94. Comparing to Falcon 9, guess what? It's the delta V is a little bit more. Probably coincidentally, it's exactly the amount more that we expect to use for landing. So that looks, my idea that the approach they use is going to be pretty similar to Falcon 9 looks at least somewhat plausible at this stage. You also notice the Starship has considerably better thrust to weight than Falcon 9 does. And that'll be a little helpful. That'll reduce the gravity losses. So we can say that its delta V is actually probably a little more, or it loses a little less, requires a little less to get into orbit than Falcon 9 does. So we know Starship can supply about 6,700 meters per second. We're looking for 9,400 meters per second total. So that means Super Heavy is going to have to supply 2,700 meters per second to Starship. And it's going to need some amount of delta V to get to return to launch site and land. And I looked around a bunch at estimates for Falcon 9 and what this might take, and didn't find anything I really wanted to talk about. There are a bunch of numbers and they're all over the place. So we're just going to leave it at that. Super Heavy, empty mass, 180,000 kilograms. The Starship on top is 1.4 million kilograms. Propellant mass, 3.4 million kilograms. What do we get? Delta V of 3,800 meters per second, thrust to weight of 114. And we'll compare that and we'll see, once again, this is very close to what we see with Falcon 9. Now there are two parts that look a bit concerning for Super Heavy. First of all, the delta V is a little low, considering Super Heavy is coming back to land at the launch site, and the thrust to weight also looks a little low. And if we look at some numbers, super heavy landing, we'd only have about 1,100 meters per second for super heavy return to land site, to return to launch site and landing. It's a little more than Falcon 9, but it doesn't look like it's a lot more than Falcon 9. And this might be a problem with my design. It might be a problem with my estimates. But that looks at least kind of not concerning, but curious. So, summary, what do we find with the reference model? Well, it actually looks like Starship and Super Heavy look very, very similar to Falcon 9 in how they'll work. It looks pretty clear that you could do Super Heavy with a drone ship landing. RTLS, I just don't think we know enough. So I'm not going to say it can't. I'm just going to say it's not obvious with the numbers I have that it can. So now that we have the reference model, we can go look at what I actually did this whole exercise for, which was the first orbital flight scenario. So what does it take to get Starship into orbit with no payload? And I elected in Starship to use it kind of in its maximal performance. I didn't try to take out propellant or take out engines. So we're going to try to use Starship with as much performance as it can provide, and that will mean that Super Heavy has to provide as little as it provides. And that will let us reduce the engines as much as possible. So if you run the numbers with Starship, same way I did before, but take out that 100,000 kilograms of payload, you get a delta V of 8,600 meters per second, which is 1,900 meters per second than we had before, and thruster weight of 1.02. So those are all great numbers for a second stage. What does that mean? Super Heavy, that means we need 1,900 meters per second less than we did for Starship. And we're going to do this by mostly taking propellant out. So that propellant being taken out, because Starship is lighter, we're overall lighter, and we can take propellant out and still keep that mass fraction, the mass starting over mass empty, high enough to get the delta V we want. And that delta V I'm going to want is only 2,200 meters per second. So we do that, we play around with engine numbers, and what do we get? If we go with 16 engines, we get a thruster weight of 1.14, and if we go with 18 engines, we get a thruster weight of 1.29. And 1.29 looks like a better one that's closer to Falcon, so I decided that was the number. So now there's also an aesthetic argument to make towards 18 engines. We expect 20 engines in the outer ring, or the outer portion of Super Heavy, and then 8 that are gimbalable, steerable in the inner ring. And if you go with 18 engines, you have precisely half of the engines in the outer ring. So it makes kind of aesthetic sense. So that's why I chose that. Now you could play around with this. You might go 10 in the outer ring and only 7 in the inner ring. That would give you reasonable results, and that might give you a nicer inner layout than 8. There's also another option they might do. There's another Raptor engine that Musk has talked about, and they've talked about building a non-throttleable Raptor. So you turn it on and it runs at full thrust until you turn it off. And here's another set of estimates for that. The ISPs go down a little, but the thrust goes way up. And since we were talking about thruster weight earlier, that's an important consideration. So what do we get from this new engine? If we're trying to do that first flight with an empty Starship, same 40% fuel load in Super Heavy, you can do it with 8 sea level Raptors and 8 of these non-throttleable ones. And maybe you go down to 7 and 8 or something like that, but something on that order. That gives you a really nice thruster weight of 1.4. And delta V pretty much identical to what we saw with the normal sea level engines with the 18. If you apply that to the reference one with the 100-ton Starship cargo, I looked and I said it's probably 8 sea level Raptors, 18 of the non-throttleable ones. And that number didn't go down really, simply because I thought they'd want to bump the thruster weight up. And that's assuming the thruster weight is actually accurate. It might be more even in the normal case. But you can see the advantage of why they'd want to go with these non-throttleable Raptors. It would not only let them reduce the number of Raptors, even in the full version, they might be able to use 2 fewer Raptors, which would be useful, but it has the potential of bumping their thruster weight up quite a bit. And that's really useful from a performance perspective. And delta V on this one, pretty much the same as what we saw with just sea level Raptors. So summary, Starship with an empty payload, I'm saying is probably going to be 18 Raptors on Super Heavy. If you go with the non-throttleable Raptor, probably 16 engines for the first orbital flight, and maybe 26 for the full payload. Depends on what thruster weight ratio they want. So that's a little short talk. Hope you enjoyed it.